Welcome back to ECE 442-542. In this video, what we're going to look at or examine is finding the z-transform of an exponentially damped cosine waveform. That's what we want to end up with. But before we go through the nuts and bolts of that, let's just try to connect that with what you've probably already seen or are familiar with, and that's the exponentially damped cosine in a continuous time setting. Here is our expression, little x of t. It has this exponential damping. The damping factor is sigma, and it's a negative sigma t, so it is decreasing with time. That gives us this exponential decay, and the oscillatory behavior is coming from the damped frequency omega sub d in the argument of the cosine waveform. Omega sub d again has units of radians per second multiplied by time in seconds will give us the radians that we want. If we Laplace transform that particular expression, we find this ratio of polynomials in S, and here we have our denominator polynomial written in a factored way that should actually very cleanly illustrate that this quadratic factor in the denominator actually has poles at S equal to minus sigma plus and minus j omega sub d. If you plug in that relationship or that value, either the plus j omega sub d or the minus j omega sub d for S in that denominator, you will see that that denominator vanishes. And writing the denominator in that form allows us to very quickly see the real part, and that real part is negative, and the imaginary part, which is the damped frequency omega sub d. The pole zero diagram for that transform of an exponentially damped cosine is shown here in the complex S plane. The poles are obviously in the left half plane. They correspond to this exponential decay. It is a damped cosine waveform, and in the cosine version of this exponentially damped sinusoid, we actually have a zero right on the real axis between the complex conjugate pole pairs, and it has the exact same distance into the left half plane for the location of the zero. The zero is at S equal to minus sigma. So now let's try, we have this understanding of the continuous time waveform in the S plane. Let's now examine where the poles and zeros are, or what the z-transform will look like for this particular time domain waveform. This is now our little x of n that we want. We've seen it for the continuous time, but now let's see where that structure actually comes from in terms of having a radial magnitude, that's the r, raised to the n. So if you're inside the unit circle, which we should be if we want a decaying exponentially damped sinusoid, r will be less than 1, and that will collapse as we raise that to higher and higher powers of n. And then we have cosine of theta sub dn, which gives us the oscillatory behavior, theta sub d having units of radians per sample. And so now with each sample, we're advancing a different amount of radian measure associated with this time domain waveform x of n. Let's see where that comes from. And we can see this, or we can connect it with the continuous time case by simply sampling the continuous time case, but we want to sample a particular version or description of that, and the description that we will use is actually complex exponentials. And we can find complex exponentials by simply invoking Euler. Here we're simply rewriting cosine omega sub dt using Euler as this combination, linear combination of complex exponentials. And when you see a complex exponential, you can simply think of the positive one now as rotating counterclockwise as t evolves, and the other one with the negative exponent is going clockwise, and they're going at the same rotational or angular rate around the origin, and their combination now will give you something that looks like a cosine waveform when you add those two pieces together. Let's now distribute that e to the minus sigma t through both terms and combine the exponents, and now we see where each of these two complex conjugate poles are in this exponential way of writing this x of t expression in the continuous time setting. So there are our pole locations. They're at minus sigma plus and minus j omega sub d. Those are in the exponents of this exponentially damped waveform. Let's now sample this or replace little t with a sampled version or chop up the time axis in intervals of one sample period equaling capital T. If we now replace little t with little n capital T in this expression for the continuous time waveform, pushing that nt through both pieces in the exponent and now factoring that single exponential term into the product of two exponentials, which is possible by the way we can combine or work with exponential factors. We now have a common piece that we can actually factor out. We factor that common piece out, and we now have in the rightmost square bracket an e to the j omega sub dt raised to the n. Again, we're just repackaging this complex exponential, or these two complex exponentials. One is the conjugate of the other, and that allows us now to see that we have an e to the j theta sub d raised to the n plus an e to the minus j theta sub d raised to the n, or that is just two cosines, cosine with an argument of theta sub dn. Because here what we've done is we've simply pushed this inside this parenthetical expression on both pieces, and so now we have e to the jx plus e to the minus jx, and that's simply 2 cosine of x. We still have this common factor out in front, which now we rewrite it so that this n pops out up above, and that e to the minus sigma cap t is where the r comes from, and as long as we have an exponentially damped waveform, r will be less than 1. We raise that to n. This 2 in the denominator cancels that 2, and here is now the connection between the continuous time exponentially damped cosine with this discrete time version, where we now have some magnitude r raised to the n cosine theta sub d n. What we want to do now is z-transform this expression, this little x of nt, and sometimes we may actually suppress the capital T. But even before we do that, let's just remind ourselves of what we have, and e to the minus sigma t gives us the blue dashed exponential envelope of decay. The cosine omega sub dt gives us this green dashed, well, it actually would oscillate without any damping, but with the blue superimposed, now we have to collapse this sinusoidal waveform down as we move to the right or to a larger value of time. And the red stem plot is now a picture of this discrete time exponentially damped cosine. And we want to now find the z-transform of this sequence of numbers, which are represented by these red stemmed values. And before we even get too far, we're going to go ahead and rewrite this cosine of theta sub dn as, now this is 1/2 of e to the j theta sub dn plus e to the minus j theta sub dn, and that's where we come up with this particular expression. That's now x of n, and again you can see that I have suppressed the capital T in my time domain expression. The capital D is actually already implicit in R, and it's also implicit in theta sub d. Remember, R was e to the minus sigma capital T, so the T is already in there, and theta sub d was omega sub d times capital T. Pushing the 1/2, or replacing or putting little x of n into the definition of a z-transform, and we're assuming that this is a sequence that begins at time n equal to 0. We have a causal sequence. It's only true for non-negative values of n. We can then start our lower summation index at n equal to 0 in this z-transform expression. And what we want to do now is actually pull that apart into two different sums. Since we have a summation right here, let's now combine the first piece and the second piece, so that we now have one with a positive e to the j theta sub dn and another piece which is e to the minus j theta sub dn. But that can also be rewritten, or we can take this common exponent out of all three pieces, which is little n, and now in the leftmost summation we have capital R e to the j theta sub d z to the minus 1, that quantity raised to the nth power as a sum, and we have a similar expression on the right hand side with a factor of 1/2 in front of each one. We can clean this up or make the writing a little bit cleaner if we just define x1 to be what I've indicated in red and x sub 2 to be the conjugate of that expression. And now we want to find these two infinite sums in terms of x sub 1 and x sub 2. And we know how to do that. Our common ratio in the leftmost is x sub 1. The common ratio in the rightmost summation is x sub 2. We need the magnitude of that common ratio to be less than 1 for that sum to converge and to be meaningful. And we know that that means then that the magnitude of x1, which in expanded form is r z to the minus 1 e to the j theta sub d, the magnitude of e j to the theta sub d by Euler, that's just cosine theta sub d plus j sine theta sub d, and we know that cosine squared plus sine squared equals 1. The magnitude of that rotating phasor e to the j theta sub d is just equal to 1. So now we need for x1's magnitude to be less than 1 and for x2's magnitude to be less than 1, we need the product of r, z to the minus 1's magnitude to be less than 1. We're assuming that, and if that's the case, then we can find a closed form expression for both of these infinite sums, and those are just 1 over 1 minus the common ratio. We now have 1/2 times the first piece plus 1/2 times the second piece. We can put those over a common denominator, which The common denominator here is just 1 minus x sub 2, or the half of the common denominator is 1 minus x sub 2. The other half is 1 minus x sub 1. We do the appropriate summation in the numerator, perform the algebra, and we actually end up then with capital X of z written in terms of x sub 1 and x sub 2 being 1 minus 1/2 times the quantity of x1 plus x sub 2 over 1 minus the quantity x1 plus x sub 2 plus x1 times x sub 2. Now we can go back and start to replace x sub 1 and x sub 2 with, in fact, what they are defined to equal. The product of x sub 1 and x sub 2, now we simply have to realize that e to the j theta sub d times e to the minus j theta sub d is really just e to the j times theta sub d minus theta sub d, or e to the 0, which is 1, or the product of x sub 1 times x sub 2 becomes r squared times z to the minus 1 squared, or z to the minus 2. The sum, which we need here and here, let's go ahead and find the sum of x1 and x sub 2. X sub 1 and x sub 2 are conjugates of each other, so we should expect something nice to result from adding those two pieces together. And now I'm hoping that after this experience with this problem, you see e to the j theta sub d plus e to the minus j theta sub d is just 2 cosine of theta sub d. Or the sum of x1 plus x2 is 2r z to the minus 1 cosine of theta sub d. Using this value for x sub 1 plus x sub 2 and this expression for x1, x2 in the formula for capital X of z allows us now to simply express the z transform of this exponentially damped cosine is 1 minus r z inverse cosine of theta sub d, where that was there's just 1 minus 1/2 of that. So we've now lost the 2 in the numerator. We don't lose the 2 in the denominator because there is no factor of 1/2 there. We simply have that scaled by 1. And now we have in the denominator 1 minus 2 r z inverse cosine theta sub d plus the product of x1, x2, which again was r squared z to the minus 2. That's one way of expressing the z transform of a complex exponential, an exponentially damped cosine waveform where the time domain signal looks like this, r to the n cosine theta sub dn. One way to write that is here in the blue box, but that's in terms of negative exponents in z. We can multiply both sides through by, both the numerator and denominator multiplied by z squared, which is z squared over z squared, or 1, and that now allows us to obtain this formula for capital X sub z written in terms of positive powers of z, and now we can maybe more easily see where the zeros are located and maybe even where the poles are located. The zeros are those values of z that cause the numerator to vanish, and I think you can see that we have 1 0 at the origin and the other 0 is at r cosine of theta sub d, and in that form we can actually sketch a pole zero diagram. The poles are actually at r e to the j theta sub d, r e to the minus j theta sub d. That gives us these two pole locations. They have a real part of r cosine of theta sub d. They have an imaginary component of r sine of theta sub d. The two zeros are real, one at the origin and one at r cosine of theta sub d. And the poles, written in rectangular form, are given by this particular factor giving rise to the real component of r cosine of theta sub d. The other piece of the denominator written in this factored form gives us r sine of theta sub d, and that's the imaginary component of those pole locations. And you should be able to perform this algebra to produce that particular denominator expression. And this is another way of writing and thinking about the z-transform of an exponentially damped cosine, and you can compare this z-plane pole zero diagram with its s-plane analog for the continuous time waveform. But I hope this now makes you feel a little bit more comfortable with where, in fact, this z-transform formula comes from.